Thank you, Chairman, for the introduction. The work I'm going to show you is about the wear behavior of an innovative zinc alloy, zinc-based alloy, and the effect that aging has on its properties. Zinc alloys are materials characterized by a good castability and a low melting point, and also by low cost. And these characteristics make them suitable for the realization of different components, from gadgets to handles. And these materials has also a low friction coefficient that is often lower than the friction coefficient that copper alloys has in different fields. So in the last years, many parts like gears, locks, rims, and so on are realized with zinc alloys, mainly because of the low cost coupled with these properties. One of the main problems of the zinc alloy is the aging, that can be defined as the decrease of the mechanical properties of the alloy in time. So the material moves towards more stable equilibrium state, and the properties decrease in time. The process is well known on the traditional zinc alloy like Zamac, and it has been studied mainly on the properties like UTS or Atlas. The process is low at room temperature. It takes years. We can say that material reach a stable condition after 20 or 30 years. But the process is enhanced by the temperatures, and considering also the melting temperature of zinc alloy, 100 degrees are often sufficient to reduce the aging time from years to hours or days. The phenomenon is present also for high aluminum zinc alloy, not traditional one, but it's less studied. In the picture, I show you one of the study of the aging phenomenon of this zinc alloy. For this reason, and to overcome the problems of the zinc alloys, in the last years a new zinc alloy has been developed to increase the mechanical property of the traditional one, to enhance the wear resistance, and to reduce aging problem, in order, as I told you before, to create material that can substitute the more expensive copper alloys. The alloy we study is a zinc 15 aluminum 1 copper magnesium alloy that was developed in the University of Brescia in 2010. We did some trial tests in the factory and in the laboratory, and we see that the alloy can be suitable to realize components both by foundry processes or by stamping and deforming processes. This alloy is characterized by a good wear behavior, a good wear resistance, a good corrosion resistance higher than the traditional alloys, and good mechanical properties as shown in this table. So the aim of the work I'm presenting you is to understand the wear behavior of this alloy, and in particular to study the effect that aging has on, first of all, the wear behavior, and also on the other properties of the alloy. To hit this goal, we started with the production of samples via spin casting samples. So we product all the samples to the test we did later. We aged all the samples at 105 degrees for different times, starting from 0 hours, the not aged sample, up to 240 hours. The temperature of 105 degrees was chosen because this temperature is a reference for the traditional zinc alloys, because the properties that the material reach after 1 year of natural aging can be reached also after 24 hours of aging at 105. We did then micro-hardness test, and salt test, and we evaluated the microstructure, and we did the wear test. Concerning the wear test, we did pin on this test with the apparatus shown in the picture, and we chose as applied load a very low load of 1 Newton, because this load is sufficient to significantly damage the material after the test. As output of this kind of test, we obtained the friction coefficient and the wear path profile measured via stylus profilometers. This measurement allowed the wear rate calculation with this formula. Moving on the result, as you can see in the graphs, the alloy is sensitive to the aging, because the hardness decreases substantially during the age. In particular, in the first 72 hours, we have the first and more persistent drop, and then the value seems to reach a stable value. The same behavior was detected after the tensile test. So both UTS and EXN decrease mainly in the first 72 hours, and then the material seems to reach a stable condition. As the UTS decrease, as visible in this graph, the elongation increases as a signal that the materials becomes more ductile. We have to consider that the maximum elongation is around 1%, so the main behavior of the material remains is not a real ductile material. The main behavior remains very good. To understand the cause of the reduction in mechanical property, we studied the microstructure of the alloy. As you can see in the picture, we can see two different phases. There are the globulus of the primary aluminum phase in gray, and in white the zinc rich phase. After the aging, we did not point out any substantial modification, neither in the type of phases nor in the morphology or the amount of the different phases. So we move on studying the fracture surface of the tensile test temples. As you can see, the fracture surface is mainly brittle. But after the aging, we observe that the aluminum rich phase indicated in both the figure with the spectrum 1 becomes more ductile, as the fracture shows the typical ductile surface with the presence of dimples. But only the aluminum rich phase shows this modification, as the zinc rich phase remains brittle. The wear test show a worsen of the material after the aging, as the friction coefficient as well as the wear rate increase after the aging. Also in this case, mainly in the first 72 hours of aging. In order to understand also the wear test result, we studied the morphology of the wear tracks, and we observed that the morphology of the tracks shows a couple of phenomena of oxidation and abrasive wear, as stretches aligning in the sliding direction are present, as well as oxidizing area inside the tracks. The morphology of the track doesn't change by changing the aging time, so the decrease of the behavior during the wear is mainly related probably to the decrease of the hardness of the material, as it is well known that decreasing the hardness of the material, the abrasive wear increases with the increases. So, concluding, we observe that the UTS, the EXN, and the hardness of the material is decreases by increasing the aging time, showing that also this material, as well as the traditional alloys, change its properties during the aging. The cause of this behavior is not related with the microstructure, as the microstructure doesn't change after the aging. But we observe that the material becomes more ductile, or in particular the aluminum rich phase becomes more ductile after the aging, justifying the increase of the elongation and also the decrease of the UTS. The wear behavior becomes is worsened by the aging, as the friction coefficient increases and the wear rate decreases too. And this behavior is related probably to the decrease of the mechanical properties, as the morphology of the wear track doesn't change in increasing the aging time. We also observe that the first and more consistent drop of the mechanical properties is, of course, in the first 72 hours. And then the material reaches a sort of stable condition that are confirmed also by the test performed at 240 hours. So, as an indication in the designing of part with this alloy, it can be really useful to define a proper safety coefficient in order to compensate the effect of the effect that the aging has on the mechanical properties. Thank you for your attention.